Good evening, everyone. How is everyone doing this evening? Why better than yesterday? I'm also well, thank you. So I think class participation this evening will be a little bit low. It seems like there's a semester test this evening. Be finding first year interesting semester test for what? So uh, let me get the semester tests. I'll tell you now. So apparently it's WTW152. It's a practical test. Ah, okay. Okay. So, few questions. So the first is just a bit of a topic question. Where do you think all the antimatter that was there when the universe began went to? I found an interesting theory on the internet that says that when the Big Bang occurred, all the antimatter and normal matter annihilated each other, and the remainder of the intersection is normal matter that makes up the current matter. Universe now, yes, I agree with it, because if you do the math, if matter and antimatter collide, that they annihilate each other, so nothing is left. So yes, that is what's left now. So another question, how was my first year? So that brings me to something I want to discuss with you first. Um, every Tuesday morning we have a departmental meeting for physics department where we discuss departmental matters and other issues, and we also catch up on each other's research and what's going on. And one thing that came to mind is the health of the students. So there's a second year student that's now suffering from panic attacks because the pressure of all the modules and studying has become too much for him. He now is considering dropping out of university. So that's one thing we would like you to encourage you is to speak to us, reach out to your lecturers, reach out to health services on campus. That's why we have health services on campus. They are there to help you. If the pressure seems too much, health services is there. If the pressure becomes too much, your lecturers is there. Speak to your lecturers. Let your lecturers know what's going on, how you feel. And to put it in perspective, first year is a difficult year, especially your first semester, because you're now coming from a school environment over to a university environment. It's a big learning curve. I know first year you are dropped a bit in the deep end. So how do you reach out to health services? I know health services currently does video calls, but you they can arrange a permit for you to go onto campus to speak to someone. So I will find out a direct contact person and I will send out notification for it. But that's why they are there. That's why they're there to help. And one thing I can add to it is first year is difficult, especially the first semester. I remember my first year, first semester, about 3 months into the semester, I was thinking to myself, whoa, this is a lot of work. What have I gotten myself into? Should I continue? Should I not continue? And my lecturers told me just to push through. If you need help, reach out to your lecturers. Your lecturers are human beings. They are there to help you. They are not nasty people. They understand what you are going through. So if you reach out to your lecturers, they will be able to assist you. They will be able to give you guidance, and they will be able to help you. And now I'm here 10 years later, and I'm so grateful that I pushed through. It's a pleasure, guys. So keep motivated. And one thing, I know it sounds silly, but it helps. If you speak to your friends about it, and basically, excuse the terms, bitch and moan about it with your friends. It's a good energy release. And one thing that you have to keep in mind is you also need to take breaks. So what I did is in my undergrad in my first year, that kept me sane was you need to have an off day in the week somewhere, and an off night somewhere. So what I did is during the week I would work. So between, if I had an off period somewhere or a gap between periods, I would work. The evenings I would work, the mornings I would work. But what I would do is Fridays would be my off days. So on Fridays I wouldn't do any work. So I will attend my classes. But if I had gaps between my classes on a Friday, I would use those gaps to relax. And on Friday evenings, I didn't do anything on Friday evenings. So on Friday evenings, I used to watch movies, play games, go out with friends, just to unwind a little bit. The only time I would work on a Friday evening is if I had a test on a Monday or assignment due on a Monday. Then I would use the Friday evening to work. And then what I also did is during the week somewhere, it depends on week to week, I would just choose one other evening a week just to relax. And during that off evening, you can do whatever you want just to relax a little bit. And that really helps to keep you sane and keeps you focused. You see, that's good. So Friday's also your off day, and that helps. And I know all your lecturers usually tell you to put in extra hours and prepare for your lectures and read a chapter beforehand. And I know you guys don't have time for those sort of things. So we as lecturers understand. So wise words. How did you overcome the fear of failure? So you overcome it. So I failed a few modules in my undergrad, and that wasn't the end. So one thing to keep in mind is if you fail a module, it is not the end. If you fail a module, one of my lecturers told me, if you fail the module, all that means is in that point of time, you are not ready for that module. So that means you don't have the skill set, you are under pressure, you might have different problems we don't even know about, problems at home, personal problems. So if you redo a module, then you already have the base knowledge for that module, and you can just build onto it and think positively. It's a pleasure to see your comment. I have the same issue. I feel like taking a break is going to make my problems with the work worse. It's important to take a break. Just if you take a break and get a good night's sleep, that already helps a lot. So, see, I've started regular exercises. I've been like, yes, that's a form of release. I'm glad to hear it. So remember, I don't know, so I know some of the other lecturers is a bit more strict in that sense, but I have an open door policies, meaning if I'm on campus and you want to pop into my office, you are more than welcome. I know being on campus is difficult right now, so that's why send me an email, you can WhatsApp me, we can arrange things. I have an open door policy. I'm here to help you guys. So I will get contact details for people at health services. I will put a notification on ClickUp, send out an email with the details. And if you don't want to talk to people at health services, you can contact me as well. It's a pleasure. So before we continue tonight's lecture, I found you asked me to go through over Kirchhoff's laws. So we, in a textbook, we touched on these laws just a little bit, but to understand completely what's going on with Kirchhoff laws, these are the three fundamental laws we use in astronomy of Kirchhoff, but Kirchhoff has a lot of other laws as well, especially in electricity. He has the voltage divider law and a current law. So when you do electricity, you will do those two Kirchhoff laws. But for our purposes, these three laws are the most important. So the first law that's described by the top image states, and is can be explained in the following way. If we have a solid, so solid surface, solid material, solid matter, even solid, so let's simplify this. If you have solid matter, a liquid, or a gas, and either one of these is under a high pressure, it gives a continuous spectrum. So in a continuous spectrum, we won't see any absorption lines and we won't see any gaps. So this is a continuous spectrum, and that's Kirchhoff's first law. Kirchhoff's second law is if we have a hot gas and it's under low pressure, it will produce emission lines, so emission spectrum. And then lastly is when we have a source that is providing us a continuous spectrum, but that source is behind a cool gas, we will get an absorption spectrum. Does that explain it, or should I go through it once again? So did Kirchhoff's laws also have something to do with orbiting? So with orbiting, we used Kepler's laws. So in the top image, a continuous spectrum, we will see this when we are looking at an object that is hot, then it can be a solid, liquid, or gas, and it must be on a high pressure. So when we have a hot, solid, liquid, and gas, and there's high pressure on it or in it, it will generate a continuous spectrum. Then law number two is when we have a hot gas with a low pressure, then we will have a emission spectrum. And then lastly, when we have a cold gas behind material that provides a continuous spectrum, then we get absorption lines. So let me find the lecture slides for this evening. It's a pleasure, guys. So last night, we ended off with two binary stars that keep stealing matter from one another, and in that way, they prolong their life. But now we're going to start the discussion of accretion disks. Around our binary star system, we will have an accretion disk, and the accretion disk is created by the matter falling in from one star. So matter flowing from one star to another can't fall directly into the star. Rather, because of conservation of angular momentum, it must flow into a whirling disk around the star. So when we have our small companion star and our large star, and the material bekend Roche lobes Dutch, we will have our material falling from the one star in this spiral pattern around this other star, and that's called an accretion disk. Another way to think about it, if you're sitting in a bathtub and you pull out the plug, you see some sort of a whirlpool motion for the water going down the drain. It's basically the same effect, but only that whirlpool is squished down into a plate. Yes, that is a vortex type motion for a whirlpool, but if you have a vortex and you squish it down into a plate, for our reference, we call it an accretion disk. So it's the same motion, but it's in a disk form. Okay, so ergosphere, I will answer that question momentarily. When we will discuss black holes in a later lecture. So how do you determine the direction in a vortex will turn? So usually our direction our vortex will turn, we can depends actually on quite a few objects. So if we have a vortex, it depends what currents are in the area and what else is in the area. So usually we can figure out its rotation by observing it, or we can figure out the rotation by creating a mathematical model. So angular momentum refers to the tendency of a rotating object to continue rotating. All rotating objects possess some angular momentum, and in the absence of external forces, an object maintains, so conserves, conversion of energy, its total angular momentum. An ice skater takes advantage of conservation of angular momentum by starting a spin slowly with her arms extended and then drawing them in. As her mass becomes concentrated closer to the axis of rotation, she spins faster. The same effect causes the slow circulating water in a bathtub to spin a whirlpool as it approaches the drain. No problem. Welcome to the class. So are Saturn's ring accretion disks? No, but we will discuss that in a later section as well. Basically, that is rock and ice particles and dust particles caught around Saturn, but we're going to discuss that thoroughly in an upcoming lecture. So this is just a demonstration. If the ice skater pulls in her arm, she spins faster. If she opens up her arms, she spins slower. Mass transferred through the inner Lagrange point in a binary system, toward a star must conserve its angular momentum. If the star is small enough, as in the case of the white dwarf, the mass will form a rapidly rotating whirlpool called an accretion disk. Can you guys still hear me? Two important things happen in an accretion disk. First, the gas in the disk grows very hot due to friction and tidal forces. The disk also acts as a brake, shifting angular momentum outward in the disk and allowing the innermost matter to fall into the white dwarf. The interior parts of an accretion disk around a white dwarf are violent places. The temperature of the gas can exceed 1,000,000 Kelvin, causing a gas to emit X-rays. And the matter falling inward can produce a vast explosion when enough accumulates on the white dwarf. The explosion of this material hardly disturbs the white dwarf and its companion star. Mass transfer quickly resumes and a new layer of field begins to accumulate. How fast the field builds depends on the rate of mass transfer. You can expect novae to repeat each time an explosive layer accumulates. Many novae take thousands of years to build an explosive layer, but some take only decades. At the beginning of this chapter, you read that the word nova refers to what seems to be a new star appearing in the sky for a while and then fading away. Modern astronomers know that nova is not a new star but an old star flaring up. After a nova fades, astronomers can photograph the spectrum of the remaining faint point of light. Invariably, they find a short period spectroscopic binary containing a normal star and a white dwarf. A nova is evidently an explosion involving a white dwarf. Let's see if we can help her. So are accretion disks the only way we can observe things like black holes? Yes. Yes, it's currently the only way we can do it. Last week I showed a small talk from a conference I was attending explaining this nicely. But I will perhaps show that video again if we have enough time at the end of this lecture. Nova explosions occur when mass transfers from a normal star through the inner Lagrange point into an accretion disk around a white dwarf. As the matter loses its angular momentum in the inner accretion disk, it settles onto the surface of the white dwarf and forms a layer of unused nuclear fuel, mostly hydrogen. As the layer deepens, it becomes denser and hotter until the hydrogen fuses in a sudden explosion that blows the surface of the white dwarf. Although the expanding cloud of debris contains less than 0.001 solar mass, it is hot, and its expanding surface area makes it very luminous. Nova explosions can become 100,000 times more luminous than the sun. As the debris clouds expand, cools and thins over a period of weeks and months, the nova fades from view. Nova Tipai Sirius erupts about every 2 decades, expelling shells of gas into space that this Hubble Space Telescope image shows in detail. The shell consists of knots of excited gas that presumably form when a new shell collides with a shell from a previous eruption. Note that this is the system depicted in figure 10.12 early in this chapter. Its name designates the third variable star discovered in the constellation by Sidus, or other words, the compass. So, what do you guys will think will happen when the sun starts burning through its fuel? Let's start a discussion. So our own star won't expand is correct. But what will happen to Earth? Yes, so basically Earth will be, you're right, Mr. Groenewold. Earth will be engulfed in the new star, or in the expansion process, not a new star, expansion process. So astronomy is about us. Although this chapter has discussed the depths of stars, it has also been discussing the future of our planet. The Sun is a medium mass star and must eventually die by becoming a giant, possibly producing a planetary nebula and collapsing onto a white dwarf. This will spell the end of the Earth. Mathematical models of the Sun suggest that it may survive as an energy-generating star for an additional 8 billion years, but it is already growing more luminous as it fuses hydrogen to helium. In a few billion years, it will exhaust hydrogen in its core and swell into a giant star about 100 times its present radius. That giant sun will be about as large as the orbit of Earth, so that will mark the end of our world. Whether the expanding sun becomes large enough to totally engulf Earth, its growing luminosity will certainly evaporate Earth's oceans, drive away the atmosphere, and even vaporize much of Earth's crust. While it is a giant star, the sun will lose mass into space. This mass loss is a relatively gentle process, so any cinder that might remain of Earth would not be disturbed, although its orbit will grow larger as the sun mass decreases. If anything is left of Earth after the sun becomes a giant, it will witness the sun's final collapse into a white dwarf. So this is where we can predict the orbits of our planets. So the Sun, so Earth, Mercury is 0.38 AUs, Venus 0.7 AUs, Earth 1 AU, Mars 1.5 AU. So in 7.58 billion years from now, the Sun is a red giant, and it is 0.9 solar masses because it burned through its fuel in expanding, so it has lost a bit of mass. And here we can see the surface of the Sun has increased to the orbit of Venus. Then in 7.59 billion years, the Sun has lost a bit more mass, and its orbit is now where Earth is. So it's quite a bleak future for Earth, and that is why there's one other reason for human species to survive, to become an interplanetary species. Yes, that will yes, that will happen as well. And because the Earth is losing mass, our orbit will gradually increase as well, and that will also cause a slowing down. So that's nothing for us to worry about. That will be in 7 billion years. But for humanity to survive, we need to become a interplanetary species. So when the sun finally collapses into a white dwarf, this might be the only remains of planet Earth. You have seen that low and medium mass stars start relatively quietly as they exhaust the hydrogen and helium, and then drive away the surface layers to form planetary nebula. In contrast, massive stars live spectacular lives and then destroy themselves in violent explosions. So now we have covered this branch. Now we're going to do the massive stars and how to become a neutron star or a black hole. So let's talk about nuclear fusion in massive stars. Stars on the upper main sequence have too much mass to die as white dwarfs, but their evolution begins much like that of their lower mass cousins. They consume the hydrogen in their cores and ignite hydrogen shells. As a result, they expand into giants, or for the most massive stars, supergiants. Next, their cores contract and fuse helium, first in the core and then in a shell producing carbon-oxygen core. Unlike medium-mass stars, the massive stars do become hot enough to ignite carbon fusion at a temperature of about 1 billion Kelvin. Carbon fusion produces more oxygen and neon. As soon as the carbon is exhausted in a core, the core contracts and carbon ignites in a shell. This pattern of core ignition and shell ignition continues with fuel after fuel, and the star develops the layered structure as shown in the following figure. So here we will have the iron core, then we can start moving up. Hydrogen shell, helium shell, carbon shell, neon shell, oxygen shell, silicon shell. So we have one layer upon layer upon layer. With a hydrogen fusion, the shell above a helium fusion shell, above a carbon fusion shell, and so on. After carbon fuses, oxygen and neon and magnesium fuse to make silicon and sulfur, and then the silicon fuses to make iron. The fusion of these nuclear fuels goes faster and faster as the massive star evolves. Recall that massive stars must consume their fuels rapidly to support their great weight. But other factors also cause the heavier fuels like carbon, oxygen, and silicon to fuse at increasing speeds. A hydrogen core fusion can last 7 million years in a 25 solar mass star, but that same star will fuse oxygen in its core in 6 months, in silicon in 1 day. So when you go over to the next fuel source or element, it becomes more and more faster. So here we can see time in years for 25 solar mass star. So here we can see the fusion of helium, hydrogen into helium will take roughly 7 million years. Helium to carbon, 5 million. Silicon to carbon to oxygen, 600 years. Oxygen to silicon, 6 months. Silicon to iron, 1 day, and the core collapse in a quarter of a second. Now we discussed nova explosions, and that causes planetary nebula. But now we're going to talk about entirely different beast, a supernova explosions. So theoretical models of evolving stars combined with nuclear physics allow astronomers to describe what happens inside a massive star when the last of its nuclear fuels are exhausted. The death of a massive star begins with iron nuclei and ends in a cosmic violence. As a star develops an iron core, energy production begins to decline, and the core contracts. For nuclei less massive than iron, such contraction heats the gas and ignites new fusion fuels. But nuclear reactions involving iron remove energy from the core in two ways. First, the iron nuclei begin capturing electrons and breaking into smaller nuclei. The gas is so dense it is degenerate, and the degenerate electrons help support the core. The loss of some of the electrons allow the core to contract even faster. Second, temperatures are so high that the average photon is a high-energy gamma ray, and these gamma rays are absorbed by atomic nuclei, causing them to break into smaller fragments. The removal of the gamma rays heavy also allows the core to contract even faster. Although the core of the star can't generate energy by nuclear fusion, it can draw on a tremendous energy stored in its gravitational field. As the core contracts, the temperature shoots up, but it's not enough to stop the contraction, and the core of the star collapses inward in less than a tenth of a second. The collapse of the core produces an immense supernova explosion in which the star's outer layers are blasted outward. The core of the star must quickly become a neutron star or black hole, the subjects of the next chapter. So here we can see the core of a massive supergiant has begun to collapse at the lower left corner of this model. Matter continues to fall inward, so the blue and green, as the core expands outward, yellow creating a shock wave. To show the entire star at this scale, the page would have been 30 kilometers in diameter. Only 0.4 seconds after becoming violent convection in the expanding core pushes outwards. The shock wave will blow the star apart as a neutron star forms at the extreme lower left corner. And we are left with these wonderful supernovas. So we can take these images we have and inspect their emission absorption spectrums to determine what they are made of. So this colors doesn't represent the actual color of the spectrum of these elements. This is just to visualize for us. So then we can determine silicon, sulfur, calcium, iron, and this is the blast wave. Yes, Mr. Lavuyo.
So I'm sure you're aware of what happens when you burn certain elements. They have a specific color that they give off.
Yes.
Would it be this, like, would you be able to say what sort of elements are in a supernova by just inspection, like just by looking?
So the elements in a supernova we determine by making use of emission absorption spectrums.
But so by using the property of like that thing that happens like when you burn the specific compounds.
So for supernova, we don't actually look at burning. So we know, like we discussed in previous chapters, some elements have emission spectrums, so they will radiate energy at certain frequencies. Some elements will have absorption spectrums that will absorb energy at certain frequencies. So by looking at entirely just at a spectrum, we can determine what elements are in a supernova.
Okay, and so just to be clear, when a supernova is happening, like it's not nothing is necessarily burning, right?
Yeah, no, nothing is in it. Nothing is burning.
Okay, thank you, sir.
Pleasure. So supernova occurs when a star with degenerate core collapses. But astronomers have found different kinds of supernova. Those that do not have hydrogen lines in their spectra are called type 1 supernova. And those that do have hydrogen lines are type 2 supernova. So remember these definitions for tests and exams. A massive star with a degenerate core can collapse and produce a supernova. These are classified type 2 and contain hydrogen lines in their spectra because those massive stars contain lots of hydrogen. But there are other ways a star with degenerate interior can collapse. A supernova can occur if a white dwarf in a binary system gains mass from its companion, exceeds the Chandrasekhar limit, and collapses. The interior of the white dwarf is degenerate, and as the collapse begins, temperature and density increase and the carbon-oxygen core begins to fuse. Because the gas is degenerate, there is no thermostat to regulate the fusion, and the entire white dwarf fuses suddenly in a violent explosion classified as a type 1a supernova. The much less common type 1b supernova can occur if a massive star loses its hydrogen-rich outer layers to a companion star. The remains of the massive star can develop a degenerate core and collapse, as described in a previous section, producing a supernova explosion that lacks hydrogen lines. A type 1b supernova is just a type 2 supernova in which the star has lost its outer layers. So now historical supernova. Because supernovae are so rare, they are difficult to observe. Astronomers must depend on historical records. Some records go back centuries, but more recent supernovae give astronomers the best evidence against which to test their theories. In the year 1054, Chinese astronomers saw a guest star appear in a constellation we now know as Taurus. It became so bright it was visible in the daytime for a month, and it took nearly 2 years to fade from sight. At the site of that ancient supernova, modern telescopes reveal a many-leg nebula known as the Crab Nebula. Doppler shift shows that the nebula is expanding at 1,400 kilometers per second, and it is now about 1.4 parsecs in radius. Dividing distance by velocity reveals that a nebula began expanding 9 or 10 centuries ago, about when the guest star was seen by the Chinese astronomers. So a bit off topic, but one of my colleagues at Hartrouw is an expert on the Crab Nebula. The hazy glow inside the expanding filaments of the Crab Nebula is synchrotron radiation that is produced by high-speed electrons spiraling through a magnetic field. We're going to discuss synchrotron radiation in more depth when we discuss black holes. So here we can see our neutron star in the middle of the Crab Nebula, and these are the filaments we see, and that is of gas rush from the side of the supernova, and this glow produced by the synchrotron radiation. So the Crab Nebula is located in a constellation we know as Taurus, the Bull, just where Chinese astronomers saw a brilliant guest star in the year 1054. Over tens of years, astronomers can measure the motions of the filaments as they expand away from the center. Doppler shifts confirm that the near side of the nebula is moving toward Earth. High-speed electrons produced by the central neutron star spiral through magnetic fields and produce the foggy glow that fills the nebula. So here we will have a magnetic field line, and here we will have photons, path of the electron, And this spiraling fast motion of the electrons causes photons to be released, and that is cyclotron radiation that produces the glow. So most of the supernova we observe today are seen in distant galaxies. Robotic telescopes search every night for supernova flaring in other galaxies. When one is seen, astronomers can obtain spectra as well as record a supernova's rise and decline in brightness to study the physics of exploding stars. If a supernova is seen in a nearby galaxy, it is sometimes possible to identify the star in earlier photos. So here we can see the same star in ultraviolet spectrum. Here we can see it in visual, so the region, and here we can see it in infrared. So the star that became a supernova was a 10 solar mass red supergiant. Type 1 supernovae are about 6 times more luminous at maximum than type 2 supernovae, and they fade more slowly at first. Type 1 supernovae decline rapidly at first and then more slowly, but type 2 supernovae pause for about 100 days before beginning a steep decline. Supernova 1987A was odd in that it did not rise directly to maximum brightness. These light curves has been adjusted to the same maximum and brightness. So this is a type 1. It will decline fast and then slowly. A type 2 supernova will remain constant a bit and then it will decrease. And that is what the supernova did in SN 1987. The star that exploded as a supernova 1987A had about 20 times the mass of the Sun. Interactions of the burst of light and gas expanding from the explosions with material lost by the star during previous stages, as blue giant and red supergiant, have produced rings around a central glow, as shown in a high-resolution image and the artist's conception. The shock wave from the explosion is now expanding into 1 light-year diameter ring of gas ejected roughly 20,000 years before the explosion. As that ring is excited, it is lighting up the region around it, revealing how the star shed mass before it collapsed. Supernova remnants. So supernova typically leave behind shells of hot gas expanding outward at velocities as high as 20,000 kilometers per second, and carrying away a fifth of the mass of the star. The shells can sweep up more gas from the interstellar medium and heat it to produce a supernova remnant, the nebular remains of a supernova explosion. A supernova remnant is an expanding bubble of hot gas created by a supernova explosion. As the remnant expands and pushes into neighboring gas, it can emit radiation at many wavelengths. Jets can be seen extending toward the left and right. So here we can see in these images. So here we can see a visual image of the remnant, an X-ray image, and here we can see another X-ray image. Supernova remnants look quite delicate and do not survive very long, a few tens of thousands of years, before they gradually mix with the interstellar medium and vanish. The Crab Nebula is a young remnant, only about 960 years old and about 9 light years in diameter. Older remnants can be larger. Some supernova remnants are visible only at radio and X-ray wavelengths. They have become too tenuous to emit detectable light, but a collision of the expanding hot gas of the interstellar medium can generate radio and X-ray radiation. You saw in a previous chapter that a compression of the interstellar medium by expanding supernova remnants can also trigger star formation. So here is a image of our wonderful Crab Nebula. And that, ladies and gentlemen, was our part on the death of stars. Do you guys have any questions before we start with the next set of lecture slides? Yes, Mr. Labuyo.
So does how long the remnant depend on the size of it?
Yes. So it will be depending on the size of the star you originally had, how much solar masses it contained.
Okay.
Yes, Mr. Visalgi.
I was reading a little bit more about the Kirchhoff laws, and I see it's a lot with the circuitry, and I see there's like these points on the circuitry, and then
Yes.
the first law, it says that if you sum up all the currents, it will equal to 0.
Yes, that is something quite different. I can explain the two Kirchhoff laws of circuitry to the class if you're interested.
Yes, please, that'd be very interesting.
Okay, let me get my whiteboard and I will quickly explain Kirchhoff's laws to you guys. I'll get it to you now. Let me just prepare a little bit for this. Okay. So yes, it will be in node analysis as well. So electrical engineers loves Kirchhoff's laws. So in Kirchhoff's laws, is usually another word for it is node analysis. So one way we can draw it is we can say this is one current. We have this over here. We have this over here. My arrowheads are not the best arrowheads ever. Another arrowhead here. Let me get out another color. We call the current flowing this way I1. We call the current flowing this way I2. And we call the current flowing in this way to the node as I3. So those are the currents. And in this point right here is our node. So what this says is if we take this node and we add all the currents, so we have I1 plus I2 plus I3 equals 0. So now when we have one of these currents, we can solve them. So manipulating this equation, so let's draw it the other way, let's modify it a little bit. And let's say, for example, I2 is flowing the other way. Then Kirchhoff's current law tells us whatever flows into a node equals whatever flows out of a node. So now this equation will become I1 plus I3 equals I2. So if you want to write it in the same format as the original equation, then we have I1 plus I3 minus I2 equals 0. And that is basically Kirchhoff's current law. So that is just an easier way to solve for variables in electronic circuits. And then he has a voltage law as well.
May I ask, what is the purpose of the node?
So the node is just, we add a node, so it just makes it easier for us to solve variables in equation.
Okay, so it doesn't have like any practical reasons.
Yes, no practical reasons for it. So the equals 0 is because it's flowing in, right? So this is one part of Kirchhoff. One thing engineers and physicists differ a bit on. I've worked the last 10 years with this. So usually a physicist will bang their heads and figure out what direction the current is flowing, because the current will usually flow from a high potential to a low potential. But when you're solving circuitry, you don't care what direction the current is flowing. If you do the math and you end up with an answer like -2 amps, all that it means is your assumption was wrong and the current is actually flowing the other way. So when you get an answer of -2 amps, you think, okay, so it's 2 amps, but it's flowing the other way than I assumed. So it's no need to figure out directions. It just helps us. And then the other one we have with this, let me just clear the whiteboard, is Kirchhoff's voltage rule. So I said like engineering math with math. That's actually quite funny. So usually the maths department usually complains that the engineers rape the normal math and make them do whatever they want. So with the other one, let's say we have our power source. We have a, let's call this a resistor 1. We call this resistor 2. And we finish our loop. And now we assume our voltages as plus minus, plus minus, plus minus. Now we have our current flowing in the circuitry this way. So we call this our current. So now we have our loop set up right. So now we can say with this as well, we can say over here is our voltage source. That could be our battery, our generator, or whatever. So this will be voltage 1, and this will be voltage 2. So when we do the math of the voltage law right now, we can now say our source equals voltage 1 plus voltage 2. Or we can write it the other way around and say voltage source minus voltage 1 minus voltage 2 equals to 0. But this equation we can multiply a bit differently, and we can say voltage source equals, we have I, because the current through each resistor will be the same, times R1 plus the current times R2, because we have our little triangle. Don't know if you guys remember this triangle. So if we want V, we cover the V and it's I times R. If we want I, we cover I and it's V divided by R. Or we cover R and it's V divided by I. So now we can simplify this further. Say this is I, R1 plus R2. And that is Kirchhoff's voltage law. Yes, so in the voltage law, when we have a serial circuit like this, so meaning only one path for the current to flow, says the current will be the same everywhere. In the previous sketch we did, we have 3 different branches, then the current will be different in each branch. Pleasure. Bringing this to mind, one thing, I don't know if any of your lecturers has, yes, Mr. Le Bouillon.
What makes the electron decide which path it's going to take when it has to choose a path?
Resistance. It will pick the path of least resistance.
But then, sir, how would it know? Because it can't necessarily see ahead.
So what happens is it happens everywhere in nature. It depends on the conductivity. Your electrons flow will always follow the path that has, let me draw a sketch, the least amount of resistance. So say, for example, we have our circuit here. It splits, and there's nothing there. It splits, and we have a resistor over here. So when our current flows through here, this way, and it comes to this node. This node, this branch over here, will have higher resistance. So it will basically see it as a wall. So instead of using more energy to climb over the wall or go through the wall, most of the electrons will go this way, and some that has enough electron flow and enough current higher current will go through the resistor.
So is it like, for example, sir, is it like a river where it's hitting a rock and then you get some like water going over the rock, but most of it will be going around it?
Yes, that's exactly it.
So then, would you say where there's a resistor, there's like quote unquote a traffic jam of electrons?
Yes, exactly it.
Okay.
So like I was saying, one thing I would like you guys to keep in mind, I don't know if any of your lecturers has told you this before. If you're working with equations, don't substitute your values from the get-go in the equations. Say, for example, just stupid example. Let's say we have an equation x equals a let's call this ay plus by squared plus z. Don't substitute your values for a, y, b, y squared, z, and x into equation from the get-go. Keep your variables in. So say, for example, we have this equation and we want to solve for y. Keep y and everything in. So what we will do is we will say, for example, x, we take out a y. We will have a plus by plus z. Then we will move over this to this side and solve everything to this side. And then at the end, you substitute your values in. The reason I say this is if we do it that way, you won't have any rounding mistakes through your equations. And also, when you start working and plugging in values, it's easy to make a mistake, especially when using different units and when you're using weird numbers. So always, when you've simplified your equation, then you plug in your variables and you get your final answer. So what we're going to do now, I'm just going to quickly upload the new lecture slides. So while I'm waiting for that to happen, I'm going to show you guys a video of what we're going to discuss next in the work.
As we've seen over the past few episodes, a lot of really epic stuff happens when a star dies. If the star's core is less than 1.4 times the mass of the sun, it becomes a white dwarf, a very hot ball of super compressed matter about the size of the Earth. If the core is heftier, between 1.4 and 2.8 times the sun's mass, it collapses even further, becoming a neutron star that's only 20 kilometers across. The neutron soup inside of it resists the collapse and prevents the core from shrinking anymore. But what if the mass is more than 2.8 times the sun's? If that happens, the gravity of the core can actually overcome the tremendous resistance of the neutrons and continue its collapse. What force can possibly stop it now? It turns out none. None more force. There is a little star is about.
Can you guys still see the video? Or yes, I thought I messed this up.
So you can only hear it.
I'll quickly try and fix it.
I talked about escape velocity. Sun, it becomes a white dwarf, a very hot ball of super.
Okay, so correct now,
As we've
guys?
seen over the past few episodes, a lot of really epic
Awesome.
stuff happens when a star dies. If the star's core is less than 1.4 times the mass of the sun, it becomes a white dwarf, a very hot ball of super compressed matter about the size of the Earth. If the core is heftier, between 1.4 and 2.8 times the sun's mass, it collapses even further, becoming a neutron star that's only 20 kilometers across. The neutron soup inside of it resists the collapse and prevents the core from shrinking anymore. But what if the mass is more than 2.8 times the sun's? If that happens, the gravity of the core can actually overcome the tremendous resistance of the neutrons and continue its collapse. What force can possibly stop it now? It turns out none. None more force. There is literally nothing in the universe that can stop the collapse. The core of the star is about to go bye-bye. Way back in episode 7, I talked about escape velocity, and it's about to become a major player in the unfolding events of the collapsing core of a high-mass star. In brief, it's the velocity at which you need to fling something off the surface of an object to get it to escape. For the Earth, the escape velocity is about 11 kilometers per second. Get something moving that quickly, and it's gone. It'll never fall back. The Sun, which has much stronger gravity than Earth, has an escape velocity of over 600 kilometers per second. A neutron star, with its immense gravity, can have an escape velocity of 150,000 kilometers per second. That's half the speed of light. Keep that in mind, and let's go back to the collapsing core of the star. As it shrinks, its gravity gets stronger and stronger. That means its escape velocity gets higher and higher. When it's neutron star size, the escape velocity is half the speed of light. But if it's more than 2.8 times the mass of the sun, the core will keep collapsing. When its size drops just a little bit more, down to roughly 18 kilometers, an amazing thing happens. The escape velocity at its surface is equal to the speed of light. And, well, that's a problem, because in our universe, nothing can travel faster than the speed of light. Not a rock, not a rocket, not even light itself. Once the core of the star shrinks down smaller than that magic size, nothing can escape. No matter can come out, so it's like an infinitely deep hole. And no light can come out, so it's black. We should come up with a snappy name for such an object. A black hole is the ultimate end state for the core of a high-mass star. Whatever happens in a black hole stays in a black hole. That region of space, that surface around the black hole where the escape velocity is the speed of light, is called the event horizon. For that reason, any event that happens inside can't be known. It's beyond the horizon for us. Black holes mess with our concepts of space and time. The math and physics of black holes is incredibly complex, so much so that even after several decades of study, physicists still argue over a lot of their properties. This has led to a lot of misconceptions about them, too. All right, let's get this out of the way right now. The sun cannot become a black hole. It takes a stellar core at least about 3 times the mass of the sun to overcome neutron degeneracy pressure. That means the original star must have something like 20 times the sun's mass or more. So we're safe from that particular sci-fi scenario. Here's another misconception. A lot of people think of black holes as cosmic vacuum cleaners, sucking in everything near them. But that's not really true. They have powerful gravity, yeah, but only when you're very close to one. The power of a black hole comes from its mass, certainly, but just as important is its size, or really, its lack of size. If you could turn the sun into a black hole, which you can't, but let's pretend you could, then the Earth would orbit it pretty much exactly as it does now. From 150 million kilometers away, the Earth doesn't care if the sun is big or tiny. We're so far away that it doesn't matter. It gets to be a big deal when you get close. Remember from episode 7 about gravity, the strength of gravity you feel from an object depends on how massive it is and your distance from its center. The closest you can get to the sun is by touching it, being on its surface, about 700,000 kilometers from its center. If you get any closer to its center, you're inside it. The material outside of your position is no longer pulling you down, and so the gravity you feel will actually decrease. But if the sun were crushed down to about 6 kilometers across, it would be a black hole. You could get much closer than 700,000 kilometers to it, and as you did, you'd feel a stronger and stronger pull as you approached it. So from far away, a black hole with, say, 10 times the sun's mass would pull on you just as hard as a normal star with that same mass. You can orbit a black hole too, as long as you keep a safe distance between you and it. Orbiting a 10 solar mass black hole would be just like orbiting a 10 solar mass star. except not so hot and bright. Black holes are weird enough without the misconceptions. Black holes also come in different sizes. The kind of black holes I've been talking about have a minimum mass of about 3 times the sun's, and might get as high as a dozen or more times the sun's mass, if the parent star was big enough. We call these stellar mass black holes. If it happens to gobble down more matter, it gets more massive, and the event horizon grows as well. The black hole gets bigger. The idea that huge black holes could form in the centers of galaxies was first proposed in the 1970s, and it wasn't much later that the first one was found in the center of our own Milky Way galaxy. We've measured its mass at a whopping 4.3 million times the sun's mass. And now we think every major galaxy has one at its heart too, and in fact may be crucial in the formation of galaxies themselves. I'll discuss those more in a future episode. Here's a fun thought. What would happen if you fell into one, say a stellar black hole with 10 times the sun's mass? You'd die. But what happens in the few milliseconds before you leave the known universe forever is actually pretty interesting. As we've seen many times in our own solar system, tides are important. They arise because gravity weakens with distance. So a big object like a moon gets stretched by its planet's gravity. The far side of the moon is pulled less than the near side. A black hole has incredibly intense gravity, so the tides it can inflict are serious indeed. They're so strong that if you fell into a stellar mass black hole feet first, the force of gravity on your feet can be millions of times stronger than the force on your head. Remember, even the meager tides of a planet can rip moons apart. When you multiply that force by 1,000,000, you're in trouble. As you fall in, your feet are pulled so much harder than your head that you stretch, pulled like taffy. You become a long, thin noodle, kilometers in length, but narrower than a hair wide. Astronomers call this, and no, I'm not kidding, spaghettification. This would happen pretty close to the black hole, just a few dozen kilometers out. If you fell in from a long distance, you'd be moving pretty near the speed of light by that point, and you'd only have a millisecond or so before it killed you anyway, so yay? Note that this is only for stellar mass black holes. Supermassive black holes are far bigger, millions or billions of kilometers across. Compared to that size, the distance between your head and feet is small, so the tides across you aren't nearly as severe. You'd fall in pretty much intact, if that makes you feel any better. But compared to either flavor of black hole, a star still has substantial size, and one that gets too close to any black hole can be disrupted via tides. In March 2011, astronomers witnessed just such an event. In a distant galaxy, a star apparently got too close to a black hole and was torn apart by the ferocious tides. As the star was disrupted, it flared into brightness, momentarily blasting out 1 trillion times the sun's energy. That's how we were able to see it, even though it was several billion light years away. But I've saved the weirdest thing for last. One of Albert Einstein's biggest ideas is that space isn't just emptiness. It's an actual thing, like a fabric in which all matter and energy is embedded. What we perceive as gravity is really just a warping of this space, like the way a bowling ball on top of a bed warps the shape of the mattress. The more massive an object, the more it warps space. Not only that, but space and time are basically two parts of the same thing, what we now call space-time. You can't affect one without affecting the other. Einstein calculated that when a massive object warps space, it also warps time. Someone deep inside the gravitational influence of an object, time is ticking more slowly than someone far away from that object. I know, it's bizarre. We think of time as just flowing, and everyone should see it move at the same rate. But the universe is under no obligation to obey our preconceptions. Einstein was right. He was right a lot. This slowing of time is stronger the stronger the gravity of the object is. So your clock ticks a bit slower than someone far away from Earth, for example. The effect is tiny but real, and we've actually measured it on Earth with extremely precise clocks. However, if you get near a black hole, the effect gets a lot stronger. In fact, black holes warp space-time so much that at the event horizon, time essentially stops. You'd see your clock running normally and you'd just fall in, bloop, gone. But someone far away would see your clock ticking more slowly as you fell in. And this isn't a mechanical or perception effect. It's actually woven into the fabric of space. To someone outside looking down on you, your fall would literally take forever. But then they wouldn't be able to actually see you. The light you emit would have to fight the intense gravity of the black hole to get out. And to do that, it would lose energy. This is very similar to the Doppler redshift I've talked about in earlier episodes, and it's called a gravitational redshift. When you're right at the event horizon, just when an outside observer would see your clock stop, They'd also see the light coming from you infinitely redshift. Your light would lose all its energy trying to leave the vicinity of the black hole, and you'd be invisible. And from your viewpoint, buckle up, because this is wow. You'd see the universe speed up, and just as you hit the event horizon, all of time would pass, all of it. And all that light coming at you from the universe would be blue shifted, becoming such high energy that you'd be fried. But since you're about to fall into a black hole, you probably wouldn't care. See, like I said, wow, black holes are so strange, with such fiercely complicated math and physics to explain them, that scientists are still trying to figure out even basic things about them. For example, some scientists argue that the event horizon as we understand it may not actually exist, and that when you apply quantum mechanics to black hole physics, you find particles can slowly leak out. We're still new at this and struggling to understand what may be the most complex objects in the cosmos. Black holes, as bizarre and counterintuitive as they are, keep popping up from here on out as we poke our noses into more and bigger astronomical objects. While they may seem scary and weird, and let's be honest, they are, they have literally shaped most of the objects we see in the universe. Today you learn that stellar mass black holes form when a very
Oh, that is cool, right? So I've looked at the comments and I thought this would actually be a cool exercise. So how do you actually calculate the mass of a black hole? You can do it in the same principle with anything in the galaxy. So do you guys want to go through the basic calculation? Okay. So you all remember this equation. So Newton's law of universal gravitation. Sorry, made a little mistake. It's G in M over R squared, where M is the mass of one object and small m is the mass of the other object. So here we have G is the universal gravitation constant. M, big M, is the central mass, so the mass of the black hole. And our small m is our solar mass, so the weight or the mass of the sun and all the planets in the solar system. And then R is the distance between the black hole and our sun. So we also know from normal classical mechanics, or another word for it is Newtonian mechanics. I prefer the word classical mechanics. We need to have centripetal force to keep an object moving in a circle. So when we have centripetal force, we call that, let's say, not to confuse everything, F cent equals mv squared over r, where the small m is the mass of the sun, and v is the velocity orbiting in a circle, so it's orbit around a black hole, and r again is the radius of the circle, meaning from the center point to the sun. So now what we do is we just equate these equations together. So we have F for the first one of the Newton's universal law of gravitation equals F of our centripetal force. Because forces are the same, we can write it like this. So now we can write this as G m over r squared equals mv squared over r. So now we want to solve this equation to get the mass of the black hole. So now if we rearrange this equation, we get m equals v squared r over g. So here we know in this equation, we know how long it takes the sun to orbit around the black hole. We know the distance from the sun to our black hole, and we know what the universal constant is, so therefore we can calculate the mass of the black hole. So you guys are happy with this?
But then, is there not like a theory that says, so like galaxies, so like even the like, for example, at the end of towards the end of the galaxy, like the outer galaxies, so that the stars there don't necessarily obey the same laws of things, because like in terms of like they should be moving at a certain angular velocity compared to the ones that are towards the inside, but that's not the case.
So when we do the evolution of galaxies later in later chapter, we will see, yes, they all follow the same laws of physics, because if something follows different set laws of physics, they will break out all hell in the universe. So what actually is happening, there's a different mechanism happening in the outer arms of galaxies, but we will discuss that in a later chapter.
So it still follows the laws of Newtonian mechanics.
Yes,
It's
it
just
does.
different that's happening.
Yeah, there's a different mechanism at play, but it will become more clearer to you when we start discussing the evolution of galaxies.
Yes, sir.
Yeah. So, Mr. Visage, I saw here about how we know the mass of the sun. The mass of the sun is, we do this the exact same way with the mass of the sun. Except of using this equation now with the sun and the black hole, we use it now with the sun and Earth. So for the sun and Earth, we can rewrite the equation again and say this is F universal gravitation, and it is G m over r squared, where the big M now is the mass of the sun, the small m is the mass of the Earth, and the Earth is orbiting the sun, so we will again have our centripetal force, and that is mv over r squared. So now again we can equate two different equations. So again we have we have this, and again we have this. So now solving for the mass of the sun, we have this. So I remember reading somewhere how to use the moon to calculate the mass of the Earth. Correct me if I'm wrong. Yes, that's correct. Another way, it's a bit more tedious, that you can do is, we know what gravity is on Earth, 9.8 meters per second squared, our gravitational acceleration. We know what the diameter of Earth is, or the circumference of Earth is, and from there we can calculate it as well. So there's a lot of ways to do these calculations.
So just to clarify, to calculate the mass of like the Earth, you would use like for example, currently in physics we currently learning about simple harmonic motion, and you
Yes.
can calculate the free fall acceleration, right? So do you also use, like, for example, you use the free fall acceleration to also calculate the force of like the mass of the Earth as well?
Yes.
Thank you.
So there's a few ways you can calculate the mass of the Earth. There's actually a very few ways we can do it. So I'm just quickly going through my notes. Okay, so let me just write it out. So I just quickly went through my old notes. So an easy way we can calculate the mass of the Earth by making use of normal classical mechanics. We know this equation. We only have one object now. S is the mass of Earth over r squared. Sorry, this is written wrong. So okay, let me explain it better. I'm going through, I'm doing it in my head faster than, I'm thinking faster than I can write. So we know our normal, we call our gravitation constant equals G M over r squared. But with this, we want to calculate the mass of the Earth, and we select the big M as the mass of the Earth and the small m as any object on Earth. So let's choose ourselves as that object. Because our mass, so let's say a normal person, let's say weighs between 70 and 80 kilograms. So 70 to 80 kilograms compared to the mass of the Earth is negligible, so you can leave that out. So now we can rewrite this equation as just G M, so we call this M, or mass of the Earth, over r squared. But we know the F of gravity is a force, and that force is 9 meters per second squared. So we can exchange this equation for G, and that equals G mass of Earth over r squared, and that r squared is where we are to the center of the Earth. So now we want this equation, so now we can rewrite this equation And by rewriting this equation, we can say gr squared equals g mass of Earth. So we can say mass of Earth equals g r squared over g. So we know what this is. This is 9.8. We know what the distance to the center of the Earth is. We know what the gravitational constant is, and we can calculate the mass of the Earth. So surprisingly, most of these calculations, if you just think about it and break it down into the logic steps that we have already learned, we can calculate most things. So yes, I can only imagine there's so many other questions arising from this. Escape velocity equation. Look, we could just refresh my mind. This is something I've done about probably 8 years ago.
So I can look for the equation if you want me to.
So I know what the equation is, but the question is how do you get to that equation? So to get that equation, you need a bit of calculus, is one way to do it. Are you guys familiar with calculus? Integrals? Okay, that's good to know. I'm just going through all my past notes. Oof. Okay, so what I will do is I've done this in quite a while. Yeah, it's the clock standing on top of my shelf that you guys are hearing. So what I will do is I will do I will show you in next week's class the derivation of escape velocity. But usually it's easy to derive one equation from another. I'm a bit rusty with it because I haven't done this in a while. But then I will show you how to get to it. But basically the formula for escape velocity is our escape velocity equals the square root of 2 gravitational constant mass over r, where m is the mass of the object we are trying to escape, g is just a universal gravitational constant, and r is the distance from the center of that body we are trying to escape.
So
Yes.
I don't know if this will jog your memory. So, but then is it not is escape velocity not when the integral has something to do with the radius reaching in infinity?
Something like that. So let me just refresh maybe. So the best way we can probably do this is by making use of the conservation of energy. So yes, it will most likely be gravitational energy. So let's quickly do this and see what we have. So we will have our, so now so just please correct me if I make any mistakes and if you see it's something I screwed up. But what we will most likely do is we will have our kinetic energy plus our potential energy of the, let's call this I for the initial part, and we will have our kinetic energy plus potential energy for the final part. So now when we simplify this further, we know when we have the initial energy, we need kinetic energy to escape the body. So that means we will have a half m, let's call this v escape squared. And we know we will have our that's one we have. So let's say, so let's not confuse our kinetic energy initial. We will call this half mv squared. We will have our kinetic energy of the final, but we know our final energy, final kinetic energy will be 0 because the velocity is arbitrarily small, so we will say this is 0. And our potential energy of our final equation will also be 0. So that means our initial potential energy will be G m over R, because we are using gravitational potential energy. So now if we plug this into our equation, because gravity is working the opposite way, this will be a minus. So this will be minus our universal rotational constant, m over R. And that's this I for initial. So that will be 0 plus 0 for our final. So now we can solve this equation. So we have a half mv squared, this is a horrible e, plus, there's a plus sign, this is minus g m over r equals 0. So now we can write this as a half mv squared equals g m over r. So now we want to solve for v squared. So now we can say this is mv squared equals 2g m over r. So now we can divide the mass of one mass away. So that is 2 G in M over Rm. So VE squared is 2G M over R. Let's continue this side. So now we can say escape velocity equals the square root of 2G M over R, and I think that's correct. Do you guys agree with my derivation? Awesome. So I think that is actually something quite fun that we did this evening. So I see our time is almost up for this lecture. So you guys is more than welcome to log off. Then I will see you all in next week's class. Good luck with the rest of your week, and good luck if you have tests and assignments. And I will see you all next week. I'll remain active too for another minute or so if you have any questions. Pleasure, guys. Yes, Mr. Fisati.